So we can derive the next equation according to the change in free energy. So change in free energy is given by delta G is equal to delta G naught plus 2.303 RT log Q. So where Q is the reaction coefficient and R is the gas constant, T is the absolute temperature, and delta G is the change in free energy, delta G naught is the standard change in free energy. As I already told you, delta G is nothing but minus N into F into E, where N is the number of electrons involved in the electrode process, F is the Faraday, E is the electrode potential. At the same time, delta G naught is given by minus N into F into E naught. As we are using delta G naught now, which is a standard, we should also use here also electrode potential, also standard electrode potential. So by substituting these two values here, we can write as minus N into F into E is equal to minus N into F into E naught plus 2.303 RT log Q. So we can bring these to the side. So we can have the expression as E is equal to E naught minus 2.303 RT divided by N into F log Q. This we call it as Nernst equation. So actually here the Q, I am saying here reaction coefficient. Just for convenience, you take a reaction as where X moles of the reactant A is combining with Y moles of the reactant B to give the corresponding products as some M moles of the C and N moles of the D. So for this, the reaction coefficient Q is given by the products, actually these two are C and D. So active mass of the C raised to the power M divided into that of D raised to the power N divided by A concentration active mass raised to the power X into B raised to the concentration of the B power Y. So once you know these, yes, we can use this particular Q value in this expression. So how we can get the corresponding, nothing but concentration of the products whether C and D, that of reactant A as well as B. The same they can also represent in the form of the electrode reactions. For example, you take the same cell where we have used the zinc as the anode, copper as the cathode. So net reaction here it is, I told you. So zinc is able to combine with Cu2 plus, where zinc is oxidized into +2, Zn +2, where the copper is reduced to Cu, from cupric to copper. So for this Q we can write it as Q is equal to, the products are zinc ions and the concentration of the copper and the zinc concentration into Cu2 plus concentration. So as per the chemical equilibrium is considered, generally here this zinc is a solid, here the copper is also a solid. For any solid substance, generally the active masses are taken as unity. That's why this particular value becomes equal to 1. This particular value also becomes equal to 1. That means we can write this Q as now concentration of the Zn2 plus divided by the concentration of the Cu2 plus. So if you substitute these two here, we can get the expression as, so E is equal to E naught minus 2.303 RT by NF log is this one. So as per representation here, the charges are +2. That's why number of moles of electrons involved in this case here, n value is equal to 2. As we are aware, this particular R is a constant, T is a constant, absolute temperature, F is a constant. The value of R is 8.314. The temperature is 298 Kelvin. This particular Faraday is 96,500 coulombs. If we substitute all these values here, we can get the expression like this also. That is, E is equal to E naught minus, this is a constant, R is 8.314, T is the 298 Kelvin and F is the Faraday 96,500. By substituting all these, we can get the expression as 0.059 by N log Q. So we can also use this expression directly instead of the above equation. As I told you here, in the case of a zinc copper electrode, so we can replace the Q in the particular case with, if you take a zinc copper electrode, I told you the net reaction here it has Zn plus Cu2 plus gives rise to Zn2 plus copper. So from this, the E value nothing but E is equal to E naught minus 0.059 divided by N values 2 log of the product is Zn2 plus concentration divided by Cu2 plus concentration. So likewise, that means from this we can say this particular E value is depending on the concentrations of the corresponding ions. So here in this case depends on a concentration of Zn2 plus and the concentration of the Cu2 plus ion. This is one of the important things that one has to remember, how the E value varies with the corresponding active mass or the concentration of the ions. So here we are taking only the metal electrodes. That's why here we got the corresponding metal ions. If you take a non-metal electrode, so definitely we can have the concentration of the non-metal ions in this case. Suppose you come across non-metal electrodes like the chlorine electrode, bromine electrode or iodine electrode, the oxygen electrode. In the particular case, we can observe the corresponding anions which are with negative charges. So in that case also, definitely the E value depends on the concentrations of the corresponding ions, whether it is cation or on corresponding anion. This we call it as the Nernst equation. So once you know this E naught value, we are saying E naught is a standard electrode potential which always remains constant, because which is measured under the standard conditions. So for the given electrode will be compulsory constant here. So this is fixed and definitely depends on the concentration of the corresponding ions. So this is a general form of the Nernst equation. In the case of the metal or again the non-metal, we can apply this. And actually here I am taking total galvanic cell. For a single electrode also we can use this expression. So as I told you here in the previously, suppose we have a metal electrode where the anodic as well as the cathodic reaction occurs correspondingly at the electrodes. Now let us see how to write the corresponding Nernst equation for the corresponding electrodes. Suppose take the same electrode which is M, which we used this as the anode here. So anodic reaction is oxidation, so which is able to give the corresponding metal ions. So this is the reactant, this is the product. So for this, what is actually Q? Nothing but product concentration by the reactant's concentration. So here M is a solid metal. So product is this one, ion. So Mn plus divided by the concentration of the metal. So for this, how I can write this Q, which is nothing but the concentration of simply the corresponding metal ions. This is anodic reaction. So here E is given by E is equal to E naught minus 0.059 by N. Where is the number of electrons involved here? Log of the N plus. Very important thing here at the reaction is oxidation. But I told you here, as per IUPAC system, so we have to use generally the reduction reaction, because this will give the oxidation potential. So if I want the reduction potential, so we can, this is oxidation potential. So if I want the reduction potential, nothing but E naught minus 0.059 by N log of 1 divided by N plus. The reason why I am writing this is, here this we got with respect to this reaction, which will give oxidation potential. If I want the reduction potential, we should use only the reduction reaction. So how to get the reduction reaction of the metal here? So Mn plus, by taking N moles of the electrons, so we are getting the corresponding metal M. So here the product is M, the reactant is Mn plus. So for this, what will be the Q? Reaction coefficient, products concentration by the reactant concentration. Anyway, this is a solid here, so concentration of the metal by the concentration of the corresponding metal ions. So this value is equal to 1. Therefore, Q becomes equal to 1 by concentration of the corresponding ion. That is the reason why we got like this. But it is mandatory that as per IUPAC system, we have to use only the corresponding reductions. Of course, we can also take this as, this is nothing but E naught plus 0.059 by N log of concentration of the corresponding ions. Because you take the reverse reciprocal of this, will get the positive sign here. That is the reason why I use this. Therefore, for a metal electrode, its reduction potential is given by E naught plus 0.059 by N log of the metal ion concentration. This is how we can write the Nernst equation for the metal electrode. So up to now, we have seen how to write the Nernst equation for the metal electrode based on the reduction reaction. Now let us see how to write the Nernst equation for the non-metal electrodes. So as per IUPAC system, I have told you we have to consider the reduction reaction. So take for example a halogen, which is a chlorine here I am taking. So chlorine half mole, by taking 1 mole of the electron, this will form chloride Cl minus. So here the chlorine is a gas. This is present in the resultant aqueous solution. So from this we can write the Q, the reaction coefficient, as the concentration of the products by that of the reactants. So here the concentration of the products is that of Cl minus ion concentration, that of the reactant is Cl2 concentration power 1 by 2. So if I take this as a unit R1, so we can write the expression, or the Q is given by concentration of Cl minus ions. Therefore, the Nernst equation in this case we can write it as E is equal to E naught minus 0.059 by, here number of electrons as per parenthesis is 1 electron. So the value of N is equal to 1, followed by log concentration of the Cl minus ions. This is how we can write Nernst equation for the non-metal electrode. So in general, if I take a non-metal as X2, so where half mole of this, by taking n moles of the electrons. So which will give the corresponding non-metal ion Xn minus. So here this is taking n moles of electrons. So we got n minus charge here, that is in the resultant aqueous solution. You make this as a gas. So for this, if you write the reaction coefficient Q, so which is given by the product is the corresponding anion, which is Xn minus active mass or the concentration divided by the concentration of the corresponding X2 power 1 by 2. This we can write. So ultimately Q becomes equal to Xn minus concentration. Therefore, for this nearest equation is given by E is equal to E naught minus 0.059 divided by number of moles of electrons is n, or simply number of electrons is n, log concentration of the non-metal ion. This is a general expression. So whether it is the first case or the second case, we can see the reduction of only single species. That's why we can get here the electrode potential of the single electrode, so which is the reduction potential. This is also reduction potential. And here this E naught, I already told you, this is nothing but standard reduction potential. Here also E naught is the standard reduction potential. So always whenever we use standard reduction potential, these values, both the case, they remains constant, because so these are measured at the concentration of 1 or active mass as the 1, so which are always fixed for the given electrodes, whether it is metal electrode or the non-metal electrode. So if you know all the different categories of the electrodes, so we can arrange them with respect to their electrode potential values, especially reduction potential values. So these together form one series of electrodes, which is called as electrochemical series. In the electrochemical series, all the corresponding electrodes are arranged in the increasing order or in the decreasing order of their corresponding electrode potential values. That series we call it as generally the electrochemical series. So in the electrochemical series, generally the top positions are occupied by the strong oxidizing agents, and the bottom positions are generally occupied by the strong reducing agents. Based on the reduction potential values, so one can decide which has to be used as anode or cathode in the corresponding galvanic or the voltaic cells. So as I told you already, the anode should be the one we should take in the left hand side, the cathode should be taken in the right hand side in the galvanic cell representation. And in order to get the EMF of the cell, I told you ER, nothing but the reduction potential of the right electrode minus reduction potential of the left electrode. So whenever we have the resultant EMF of the cell as positive, then only the corresponding cell reactions will be spontaneous. In order to have these kind of things, definitely in the galvanic cell, the electrode which is having the smaller value of the reduction potential should be taken as anode. At the same time, the electrode with the higher value of the reduction potential should be taken as the cathode. Then only ER minus EL becomes positive. That's why, so one, if you have an idea about the corresponding total electrochemical series, so one can decide among the set of the electrodes which can be used as cathode and which can be used as the anode. And ultimately, the electrode potential that generally decided by the concentration of the corresponding ions. So which is a fixed here for the given electrode. So as the concentration of the ion changes, ultimately the electrode potential values also generally changes. This is how we can write the corresponding nearest equation for both metal as well as non-metal electrodes. Let us see how we can come across about the various aspects of this particular chapter, that is the relation between electrode potential and the equilibrium constant. E is the electrode potential and K is the equilibrium constant. And I already told you, whenever we come across about Nernst equation, we have derived the expression from delta G. So delta G is equal to delta G naught plus 2.303 RT log Q. From this we have derived. There I told you Q is the reaction coefficient. Here the reaction coefficient generally can be greater than equilibrium constant K, or this can be less than equilibrium constant K, or this can be equal to equilibrium constant. So whenever we come across the stage, we are expressing this as the state of equilibrium. In the state of equilibrium, generally we can observe a reversibility of the process. So whenever we achieve the corresponding equilibrium stage, in such a case delta G becomes equal to 0. That means at equilibrium delta G value is equal to 0. That means if you substitute this here, we can have the expression as 0 is equal to delta G naught plus 2.303 RT log Q. But here whenever this is equal to 0, so definitely the Q becomes equal to K. That means here we have to replace this Q with K, where K is the equilibrium constant. So from this we can have delta G naught is equal to minus 2.303 RT log K. But this we know is nothing but minus N into F into E naught minus N into F into E naught is equal to minus 2.303 RT log K. So we need expression for K actually. So we can have minus minus get cancelled. So from this, the value of log K is nothing but N into F into E naught. N into F into E naught divided by 2.303 RT. So from this, how to get the value of K? So this K is nothing but anti-log of N into F into E naught divided by 2.303 RT. This is how we can get the expression for the equilibrium constant. So whenever we want the equilibrium constant, so first of all from this we have to start where at the stage of equilibrium delta G will be equal to 0. At the same time this Q becomes, where Q is the reaction coefficient, will be equal to the equilibrium constant K. So from that we can get the expression for K as usual. This is the expression for K or equilibrium constant. Yeah. And I told you generally there will be two types of the cells, electrolytic as well as the galvanic cells. In the case of electrolytic cells, with the use of the external potential, the corresponding chemical reactions will take place. So this is, from this we can say the chemical energy is produced by the consumption of the electrical energy. So this can be related with reference to the Faraday's laws. Now let us see what are Faraday's laws.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.